Hello, in this next video in our Tinkercad Circuits Lab series, we will be looking at NPN bipolar junction transistors, or BJTs. Specifically, we will be building something that allows us to demonstrate the different operating regions of the transistor, going from cutoff to the active region to the saturation region, and we will be demonstrating how a transistor can allow you to control a higher power, higher voltage, higher current load with a lower power, lower voltage, lower current power supply. As usual, this video is a companion to my Intro Circuit Theory playlist. This is where we go through the circuit diagrams and the math for many of these circuits. And then in this playlist, we are building them in a circuit simulator environment called Tinkercad that runs in a web browser. So if you aren't familiar with BJTs or you haven't watched this video yet, go find this link in the description. Check that out. You will learn about the different pins of a BJT, the base, the collector, and the emitter, and the relationship between voltages and currents on those pins and everything. Again, so go check that video out first. For the theory, here we are going to focus on physically constructing the circuit. All right, as usual, we will be starting out with a breadboard. And the nice thing about Tinkercad is that if you mouse over the breadboard holes, it highlights the other ones that are connected. So if you don't know how to use a breadboard, you might want to go back to some of the earlier videos in this playlist. At this point, I'm going to assume you know how to do that. We are going to go over to our parts library and find the NPN transistor, drag that out. And again, nice thing about Tinkercad, it labels the pins. And if you mouse over them, you will see collector, base, and emitter. If you are doing this with a physical breadboard and a physical transistor, check the datasheet for your transistor. The pinout is not always in this order, so if you just assume it always goes collector, base, emitter, you could wire something wrong and damage your circuit. I am going to rotate this guy, so each pin is going to go in its own row, like this. And our goal, we're not doing a microcontroller or anything in this video, is just to connect a load, so I'm going to put an LED with a current limiting resistor and a base resistor separately so we can measure the current into the base and into the collector, and we can see the relationship between those two quantities. So for a power supply, I'm going to choose something like a 4x AA battery pack. If you're doing this in a lab, you may be using a benchtop supply, but not going to bother pulling out the benchtop supply in Tinkercad. Just going to do this with the 4x AA battery pack, which gives me about 6 volts. Going to wire that up to the breadboard buses. And then first thing I'm going to do for my transistor is connect the emitter to ground. Now on a physical breadboard, this transistor would be standing straight up, and I could kind of put the jumper wire behind it here, the way the part is angled in Tinkercad, so you can see the front. That kind of obscures some of the wires, so I'm going to go ahead and connect my emitter to ground like that. And I am going to, again, connect an LED as the load in series with the collectors. So I'm going to, whoops, wrong button. I wanted to rotate my LED there. And we have other videos on this channel about calculating the current limiting resistor value for an LED. So I am not going to bother doing any math here. I'm just going to slap on, say, I don't know, a 330 ohm resistor in series with this LED and connect that to power. But you can see if I run the simulation, LED is not on, nothing is happening because I do not have any current flowing into the base yet, and I need that to turn my transistor on, which reminds me, I didn't actually just want to have the LED, I would like to have a multimeter in series with the LED to measure current. And again, have some earlier videos about how to properly connect a multimeter to measure series. This is something students have trouble with sometimes. So again, go back and check out those earlier videos if you are not sure how to do that. Here I have connected a multimeter in series, which will measure the current through this LED. But again, right now, no current is flowing because my transistor is not on. So what I am missing here is connecting the base to power, but you don't want to wire your base directly to power or you're going to blow up your transistor. You need a base resistor. And again, go back and check out the theory video if you'd like to see a little more behind this. I'm just going to go with the default value of 1 kilo ohm, connect that to power, and now we will see if I start the simulation, my LED turns on and I have some current flowing through the LED, which is coming from power through the LED, into the collector, and out the emitter, which is separate from the current that is flowing into the base. So I would like to add a multimeter there as well to measure the current flowing into the base. So I'm going to pause here. I don't want to make that common mistake. Again, I see a lot of students make when trying to measure current, doing this, putting both multimeter probes in the same row and thinking, oh, it's in series, so I should be measuring current, and then starting the simulation or turning your physical multimeter on and seeing that you're getting 0 amps for some reason. And clearly the LED is on, current is flowing through the LED, which means I must have current flowing into the base, but why am I measuring 0 amps? And that's because the 2 multimeter probes are in the same row, so they are shorted together. The current does not actually need to physically flow through the multimeter in order to flow through this resistor and into the base. So remember that to measure current in series, you need to break the circuit by moving this jumper wire to a different row and then put the multimeter leads in series with what you were trying to measure. So now the current has to flow through the multimeter to get to this resistor and go through the base. So now if I start the simulation, we will see that I have a small current into the base and a larger current into the collector. One of the nice things about doing this in Tinkercad is we can add yet another multimeter. So normally when you're doing this in a physical lab, you're probably only going to have 1 multimeter available, let alone 2 or 3. So I'm going to put this one in series with the emitter. Whoops. Helps if I don't delete my entire breadboard by accident. Just wanted to delete that jumper wire. Going to put this one in series with the emitter. And then what you should remember if you watched the corresponding theory video about this is that the collector current plus the base current should equal the emitter current. So here we go. We see that I'm getting 12 milliamps into the collector, 5.23 milliamps into the base, and then those add to give me 17.2 milliamps out of the emitter. Now, where I think this demonstration is really most useful is in adding a potentiometer, which allows you to really clearly highlight the different operating regions of a transistor. So I'm going to move things around a little bit here, delete those multimeter wires, and I'm going to add a potentiometer in series with my base resistor. And instead, I don't just want to put a potentiometer here if you're doing this on a physical breadboard, because if you turn the resistance all the way down to 0, then again, you're going to blow out your transistor. So you want kind of an extra static safety resistor there, just in case. In Tinkercad, I could omit this and it wouldn't really matter. So I'm going to give this some low value, like 100 ohms. And I'm going to connect this in series with just one of the outer pins and the wiper of my potentiometer. I'm going to leave the 3rd pin unused. So here, I don't know, give these another color, make these guys green. And then again, put that in series with my multimeter and connect the multimeter to power. So now, when I turn this on, this lets me vary my base resistance. And again, with some minimum fixed value there so I don't blow out the transistor if I turn the potentiometer all the way down to 0. And what we will now see if I start the simulation is that I can turn the potentiometer to change all 3 currents at once and highlight the different operating regions of the transistor. We see that there is a region where when I turn the potentiometer, the base current and the collector current both increase proportionally, so I'm in the active region, but eventually the base current keeps going up and the collector current does not, so I am in the saturation region where the transistor is saturated, and again, even though the base current is still increasing, the collector current is saturated or maxed out and not going up anymore. And I can fiddle with the values of the potentiometer and the fixed resistor to maybe change those currents a bit, but again, the conceptual or qualitative relationship is going to be there. So maybe if I increase this to something much bigger, 10 kiloohms, and start the simulation again, we see how my default or initial current value there is a little different. And now when I go up, let's see, I'm still saturating it around that close to 12 milliamp value. So again, If you were doing this with a real resistor, you'd have to be a little more careful about what the minimum resistance values are here, because you don't want to blow out your... Sorry, I think I just said resistor instead of transistor. Real transistor, you don't want to blow out your transistor by letting too much current flow into the base. One of the advantages of doing this in Tinkercad is you can kind of mess around with that and you're not going to damage anything. But again, this is a very nice way to get visual feedback with 3 multimeters at once, which again is sometimes going to be a pain to do in a lab setting where there's just 1 multimeter per lab bench or group. And the LED kind of gives you that nice visual feedback in addition to the multimeter reading, because the brightness simulation isn't perfect in Tinkercad. Again, it's still kind of not really showing the brightness change when I'm down there around 6 milliamps. But if you do this with a physical breadboard and physical LED, you'll be able to see the LED go from off to dim to fully lit up, and then you'll see how the LED brightness doesn't keep increasing because that current is not increasing even though the base current is increasing. The other nice thing you can do here is demonstrate how a transistor allows you to use a lower voltage control signal to control a load that requires a higher voltage power supply. So let's say I'm going to drop this battery pack down to just 1 battery. And if I run this now, we see that I'm not actually really getting any current through the LED because my red LED requires more than 1.5 volts. But let's say that I actually wanted to have 3 LEDs in series. So I'm going to add 3 LEDs here. So that's going to be, if it's 2 volts per red LED, then that's going to be at least 6 volts that I'm going to require through these LEDs. And I'm still going to have my current limiting resistor there. And again, if I try to hook that up to my 1.5 volts, it's not going to work. I don't have enough voltage to power those LEDs. But if I add, let's find the DC power supply here, the benchtop power supply, and I'm going to hook that up over to my other breadboard power buses. Give my entire circuit a common ground, but keep the 2 positive voltages separate because I don't want to short 12 volts to 1.5 volts. So I'm going to set my power supply to 12 volts, and I need to remember to move my multimeter probe over here to my higher voltage power bus. And now when I run this, I should expect to see all 3 of these LEDs light up. And again, now I am getting current into my collector again, despite the lower voltage supply and much lower current going into the base. So this is really when transistors are used with a microcontroller. So again, I didn't bother putting an Arduino or a microbit or any of the other Raspberry Pi, which is technically a computer and not a microcontroller. That's a different story. But Tinkercad does let you use these things. I have plenty of other videos about the Arduino. But the basic idea is that the individual pins on the Arduino give you a 5-volt digital signal. You can turn them on and off, but they cannot provide very much current. They can, depending on the model of the Arduino, provide up to about 20 milliamps, which is enough to drive an LED directly, but not enough to drive a motor directly, or if you need 12 volts because you have a bunch of LEDs in series. The 5 volts from the Arduino is not enough to power that. So the Arduino can provide this lower power, low current control signal into the base of a transistor, again, to kind of act like that electronic control valve, like a faucet or a hose or something, that is controlling the larger current, higher power flow through a bigger load. All right, that's it for this video. In the next couple videos, then, whoops, it doesn't want me to delete the Arduino. We will look at doing pretty much the same thing with a MOSFET, which is a voltage-controlled transistor instead of a current-controlled transistor, and then look at how you can combine multiple transistors to build something called an H-bridge to control the direction of a motor.